This is Donna Nelson at the University of Oklahoma, making a lecture for my organic chemistry class. So in this lecture, we will discuss amines. So the first lecture will include the introduction to amines, nomenclature, and properties. Then we'll look at the preparation and reactions, some reactions of amines, and then we'll go on to other reactions of the amines. So let's get started. So amines are derivatives of ammonia. And so you have three classifications: primary, where you have one alkyl group on nitrogen; secondary, where you have nitrogen bearing two alkyl groups; and tertiary, where you have the nitrogen bearing three different alkyl groups. And you can see the abbreviations for primary, secondary, and tertiary here in this box. There are naturally occurring amines with nitrogen in a ring, and these are called alkaloids. Here the nitrogen is in a ring, nitrogen is in a ring, nitrogen is in a ring. And many of these are extremely important and very active in the human body. Some of these I know you're going to be familiar with. So if you've ever been around someone smoking, you're familiar with nicotine. Some naturally occurring amines in which the nitrogen is not in a ring, these are still just called amines, even though they may be very active in the human body and very important to the human body. They're still just called amines because the nitrogen is not in a ring. The trigonal pyramidal nitrogen atom of an amine carries a partial negative charge on nitrogen, because nitrogen is electron withdrawing. Its electronegativity is just below that of oxygen. Nitrogen and chlorine have about the same electronegativity. And so you can see here in this diagram, you can see that the nitrogen is colored in red, which indicates that it is higher in electron density, and the methyl groups are more in blue, indicating they are deficient in electron density, because the nitrogen is withdrawing electron density through the carbon-nitrogen bond onto itself. It is higher in electronegativity. So the lone pair on nitrogen is going to be freely available for reactions. The nitrogen can pick up a proton and function as a base by doing an attack on the proton, giving you a protonated amine. Nitrogen can also function as a nucleophile by doing an attack at carbon. Here you see that in the chloromethane. You can see that lone pair on nitrogen attacking carbon. So that's the difference between functioning as a base, in which the nitrogen attacks the proton, or functioning as a nucleophile, in which nitrogen attacks carbon. And still you wind up with an ammonium ion, because nitrogen is bearing a positive charge in both cases. Now, the nomenclature of amines, the IUPAC nomenclature, allows for two different ways for naming primary amines. You can name the alkyl group ending in YL, followed by the suffix amine, ethylamine, isopropylamine, cyclohexylamine. More complicated primary amines are named as alkanamines. They are named in the same way as alcohols, but the suffix amine is used instead of OL. So this is an heptonamine. You can see 1, 2, 3, 4, 5, 6, 7, and you can see that the numbering starts at the end of the molecule to give the carbon bearing the highest priority functional group, which in this case is NH2, the lower possible number. You could start numbering over here, but that would put the nitrogen at the 6th position, and the goal is to give the highest priority group, which is the NH2, the lowest possible number. So the nitrogen is at the 2 position, 1, 2, 3, 4, 5, 6, 7, and you have the 2 methyls at the 4 and 6th position. So it's a 2-heptonamine, and it is 4,6-dimethyl. So these have the configuration at the 2 position. You can see we have 2 chiral carbons. At the 2 position, you have the R configuration, and at the 4 position, we have the R configuration. So this is named as 2R, 4R, 4,6-dimethyl, 2-heptonamine. The 2 indicates that that's where the nitrogen group is attached. We can use the term amino for the nitrogen group as a substituent. Here you can see you have an amino group and an alcohol functionality. The alcohol functionality is the higher priority functional group, and so this is named as the alcohol. It is 1, 2, 3, 4 amino butanol. And here the amino group, the NH2, is at the para, ortho, meta, para. So this is at the para position. It's para to the carboxylic acid group. So this is, the name is para amino benzoic acid. If the amine is directly attached to an aromatic ring, so the parent name is aniline. So this is aniline. This is ortho, meta, para. So this, the chloro is in the meta position, metachloroaniline. Here, this has 2 different functional groups. It has the fluoro and the ethyl. So the aniline is the nitrogen is the higher priority group, just as it was over here. Nitrogen is higher priority than the halogen. Remember, halogens have a very low priority at the same level as alkyl groups. So here, the fluoro and alkyl are lower priority than amino, and so this is named as an aniline. And so this, the carbon bearing the highest priority group is automatically in position 1. So this is 1, 2 fluoro, 5 ethyl aniline. So you have to put this in alphabetical order: 5 ethyl, 2 fluoro, aniline. So when it comes to secondary and tertiary amines, you name the alkyl groups in alphabetical order, followed by the amine suffix. Use di and tri if there are more than one of the same group. So here we have a methyl, an ethyl, and a propyl, and you have to list those in alphabetical order: ethyl, methyl, propyl, and this is diethylamine, trimethylamine. For more complicated amines, you find the carbon parent chain. That's going to be the longest carbon chain that bears the highest priority group. And the smaller groups attached to the amine are named as alkyl groups. So this is 1, 2, 3. So the nitrogen is in the 3 position. 1, 2, 3, 4, 5, 6. There are 6 carbons in this. So this is going to be an hexanamine. And you have the 2 chloros in the 2 position, 2,2-dichloro. And up here we have an ethyl and a methyl. Those are listed in alphabetical order. This is N-ethyl and N-methyl to indicate that ethyl and methyl are attached to nitrogen. And you can see you have 1 chiral carbon, which has the S configuration. So there's a lot to figure out in this name. So this is S, 2,2-dichloro, N-ethyl, N-methyl, 3-hexanamine. Now, the properties of amine, they're sort of similar to those of alcohols because the molecule contains a highly electronegative atom bearing a lone pair. And so there are ways in which amines interact in the same way as alcohols, and we'll discuss those in just a moment. The bond angles around the nitrogen are about 108. Those will change slightly depending on the steric hindrance of the alkyl groups. And so, but this is an sp3 hybridized orbital usually. And so the carbon-nitrogen bond lengths are 147 picometers, which is 1.47 angstroms. That's slightly shorter than a carbon-carbon bond, but longer than a carbon-oxygen bond. And so the electronegativity of the nitrogen is in between that of a carbon and an oxygen, and that affects the bond lengths. So when would the nitrogen be sp2 hybridized? Well, it'll be sp2 hybridized when the nitrogen is in conjugation with a pi system. And so the lone pair here will interact with the p orbitals or the pi of the pi system or the pi system. And so in that conjugation, this will have to, the lone pair will have to occupy a p orbital. And so the nitrogen would become sp2 hybridized in order to do that. Nitrogen atoms with 3 different alkyl groups are chiral. Here you can see the chirality, but they're not optically active because the energy barrier for inversion is very low. So you can see that the energy barrier for inversion here is 25 kilojoules, very low, easily achieved at room temperature, so pyramidal conversion occurs very rapidly. And here you can see it has to go through a transition state in which the molecule is planar. And you can see the p orbital here. Amines with fewer than 5 carbons are typically soluble in water. That is because the nitrogen, when it of a primary or secondary amine, will have at least one NH bond, and so therefore it will be capable of hydrogen bonding. It can be either a hydrogen donor or a lone pair donor in the hydrogen bonding, both simultaneously even. And so for comparison, 3 molecules are chosen here that have similar molecular weights. Remember that the boiling points of molecules are impacted by their molecular weights in a way such that the boiling point increases as the molecular weight increases. And so these are chosen because they have very similar molecular weights. So the molecular weight difference here is going to be to exert a negligible effect upon the boiling points. And so the impact on the boiling points is coming purely from the atoms involved in the molecule. And so here you can see what we're actually comparing is CH3 versus NH2 versus OH. And so you can see that the boiling point is increasing greatly as we go from carbon to nitrogen to oxygen. And that's because here you're going to have a great deal of strong hydrogen bonding. Here you're going to have less hydrogen bonding, and here you will have no hydrogen bonding. You can see these molecules have the same molecular weights, and so propylamine has a boiling point of 50 degrees centigrade, which is quite high because of the hydrogen bonding. Methylamine has 34 because there's less hydrogen bonding, but that is still higher than trimethylamine because here you have no hydrogen bonding, so its boiling point is at 3. So remember, the boiling point, what that's indicating is it's indicating the amount of intermolecular interaction. And so the more tightly that the molecules are bonded to each other or attracted to each other, the higher the boiling point, because more energy will have to be put in order to overcome those intermolecular associations. Many small molar mass amines, so these are small, relatively small amines, have unpleasant odors, smelling like, say, rotting fish. Putrescine and cadaverine are the common names for these amines, and I think the names speak for themselves. So, amines are stronger bases than alcohols and ethers. They can be readily protonated by strong or by weak acids, and so this is demonstrated here. You can see the nitrogen is picking up this acidic proton. This is, after all, a carboxylic acid, and so you would expect the amine to be protonated by the carboxylic acid. However, what this is showing you is that the nitrogen does have a strong attachment to the proton, so the pKa of the protonated amine, so this is the conjugate acid here, is 10.76, indicating that it has a very low acidity compared to that of the carboxylic acid, which is 4.76. So the equilibrium lies far to the right, indicating that the carboxylic acid tends to give up the proton and the amine tends to accept it. So this is the more stable situation here, where you have the carboxylate and the ammonium ion. So it's just a good idea to remember that the pKa's of the protonated amines are generally, 10 to 11, as is this one. Here, this is a table showing the basicity of amines. Here you can see the pKa's of the protonated amines, 10.6, 10.6, 10.6, 10.7, corresponding to methylamine, ethylamine, isopropylamine, cyclohexylamine. So these are the primary amines. Over here you see some secondary and tertiary amines, and the pKa's are 10.7, 11, 9.8, 10.8. So once again, they're in the range 10 to 11, just as you saw on the previous slide. Now, when we get to amines where the lone pair is in conjugation with the pi system, you have a lower pKa. So here, in each of these cases, the lone pair is in conjugation with a benzene ring. And so this molecule, this protonated amine, is going to be much more acidic. The pKa is down around between, for these, it's close to 5, 4.5 to 5. And so the reason that these are so much more acidic is, just as I said, the unprotonated amine has the lone pair in conjugation with the pi system. So there is this tendency for the protonated amine to give up a proton. It will be more acidic because it will give up the proton in order to allow the lone pair to be in conjugation with the pi system. You have more resonance structures available that way, and so it's a more stable situation. So these are more acidic. Over here, you can see that this is even more acidic. This protonated pyrrole is even more acidic because when the proton is given up, pyrrole has aromaticity. And so when the pyrrole is protonated, that breaks up the aromaticity. The protonated pyrrole is no longer aromatic, and so it is quite acidic, so that it can, the unprotonated amine can achieve the aromaticity, which stabilizes the molecule a lot. And so that acidity is shown in this very low pKa of 0.4. The pyridine, on the other hand, this lone pair does not participate at all in the actual pi system. This pair of electrons is in an sp2 hybridized orbital lying in the plane of the molecule, and so this sp2 hybridized orbital is actually pointing away from the pi system. And so when it becomes protonated, it's giving up the proton has nothing to do with achieving or failing to achieve aromaticity. Both of these molecules will be aromatic. And so the pyridine behaves much more like a typical amine in its pKa, a pKa of 5.3. The properties of amines. Amines with more than 5 carbons are only slightly soluble in water. That is somewhat similar to the situation with alcohols. What is happening is the nitrogen is having, which will, where the nitrogen carbon bonds are polar, and so the nitrogen, which can interact with the water easily, the nitrogen will be in the polar end of the molecule, and so the nitrogen will literally just have to drag the rest of the molecule, the nonpolar end, into the water. And if the nonpolar end is more than 5 carbons, it won't be very soluble in water. Whenever a little bit of acid is added, the nitrogen becomes protonated, and so you have ammonium ions, and those are cations, and there will be counter ions, and so they are going to be soluble in water. That means that can be used to extract the amine and separate it from the organic impurities using aqueous acid and converting them to the corresponding ammonium ions. And so that means that the ammonium ions will be soluble in water, and the organic impurities will not be. And so you can separate the two phases, and then your amines will be in the aqueous phase, and the organic impurities will be in the organic phase. The pKa of most alkylamine conjugate acids, the pKa's are between 10 and 11, as I mentioned earlier. The arylamines are less basic than alkylamines. The lone pair is delocalized into the ring, and so this gives more resonance structures. Arylamines are less basic than alkylamines. The lone pair is delocalized, as I just said. You can also see the impact of groups attached to the phenyl ring. So methoxy groups are electron donating, as you have seen, and so that is going, when the methoxy increases the amount of electron density here, and it will also increase the amount of electron density on nitrogen. And so it makes this pair of electrons more available to participate in bonding a proton. And so here, cyano, on the other hand, is electron withdrawing. So it will pull the pair of electrons in onto nitrogen and make this lone pair less available to pick up a proton. And so you can see the impact of the electron donation to make this molecule more basic, or the impact of electron withdrawal to pull the electron density off of the proton and make this molecule more acidic. So here we have the amide. You can see the pair of electrons on nitrogen is available to form a carbon-nitrogen bond. The pair of electrons moves up onto oxygen, so you have two resonance structures for this amide, and you can see the higher electron density on oxygen. At physiological pH 7.3, amines exist primarily as ammonium ions. So at 7.3, the nitrogen has picked up a proton and becomes the ammonium ion. You can remember the Henderson-Hasselbalch equation can be used to calculate the ratio of amine to ammonium ion at a given pH. So that's, in this first lecture, that's our introduction to amines. Next, we'll go on and look at the reactions of amines in the next two lectures.